Thank you so much, Bao, and thank you for a very nice introduction. Thank you, everyone, for being here. And I'm very, very excited today to talk to you about our work in strain and halide perovskites and solar stability. So without further ado, I'm going to start. I come from the Nanostructured Materials for Photovoltaic Energy group at the Catalan Institute of Nanoscience and Nanotechnology in Barcelona. And as Bauman's mentioned, I'm a PhD student here since 2021, and I'm originally from Sweden. And here you can see a part of our group with my supervisors, Monica and Sonia. And the group is very focused on the stability of solar cells, especially including perovskite solar cells. And apart from being Monica being a leader in promoting good practices in stability testing, they have also seen progress in bulk and interface additives that can improve the stability of perovskite solar cells. My focus is on in-situ characterization, which has the aim of being a technique to be used in parallel or alongside operational stability testing. Today, I'm going to give an introduction to in-situ characterization, a little bit of our strategy when performing these kind of measurements. I'm also going to talk a little bit about the cells that we've been testing and about strain, including what we observe when we use an additive engineering modification in our devices. And I'm also going to walk you through in-situ experiments with light and bias voltage, including X-ray diffraction, photoluminescence, and electrochemical impedance spectroscopy. Here you can see some of the publications mentioned in this talk. Before we begin, I hope that you are familiar with the perovskite crystal structure and some of the advantages with halide perovskites, such as their possibility to be processed from solution and adapted to flexible substrates, which makes them a good candidate for a new generation of photovoltaics that can lead to new applications and that can also be fabricated in a less costly and more localized way. In our laboratories, we consistently have efficiency between 17 and 23% power conversion efficiency. And I want to mention that this is especially with stability in mind, as that is our main focus, because we believe that there's a big need to reach the 25 years warranty mark for the lifetime of perovskite solar cells as soon as possible. And in order to do this, it's important to improve stability testing in a way that it can become easier, it can become more reproducible and more reliable. And we find it really important that it should also be accessible so that people can perform more advanced stability testing alongside their operational stability. So that the methods that we develop should be preferably on full perovskite solar cell devices, and they should be able to be using more common laboratory equipment without going, for example, to a synchrotron. And finally, it would be an advantage if the characterization methods are faster. So the ISOS protocols were developed to guide the researchers when they are performing stability testings in order to include most of the relevant stressors where effects are observed on perovskite solar cells. And in our lab, we can do continuous illumination operation under controlled conditions, such as nitrogen atmosphere. We can also do different temperature stressing. And we also have an outdoor testing facility on the roof of our building. I'm more dedicated to this plus sign over here. And I find it important to mention that in a perovskite solar cells, there are many sensitive layers. And of course, there's also encapsulation strategies, something that we've been working quite a lot on in our group as well. And in this work, we didn't use encapsulated devices, but all of the measurements are performed in nitrogen environment or nitrogen flow to account for the full device as much as possible. Another challenge that we have that we encounter is how to relate the perovskite intrinsic properties to the full device properties. So if we see some degradation that is related to perovskite intrinsic instability, it's difficult to be sure if this can be remedied by changing something in the device stack, or vice versa. If something is going wrong in the device, it can be difficult to know if it's something that is wrong with the perovskite or something that's wrong with the device stack. To gain more insight into perovskite degradation and also into how to perform in-situ and operando characterization, we performed a quite extensive review of the literature, where we just took into account works that used in-situ and operando characterization with physical and chemical information. So I really recommend our review to get a little bit of a sense of synergetic and competitive effects among stressors, as well as parallel effects, to try to understand how different stressors can be combined to produce certain conditions in our solar cells that can lead to better testing conditions. In our case, we were a bit interested after our review to combine these two stressors. So we wanted to use illumination and voltage bias in combination. And when we apply these stressors, we would expect some effects such as segregation, crystal decomposition, and maybe morphology changes and changes at the interface, so it's related to defects. There have been reports of instability related to bias voltage for a long time. This includes hysteresis and transient effect, stability issues at open circuit voltage compared to at the maximum power point when doing operational stability testing, ion migration driven by electric fields, and also reversible and irreversible changes when applying a forward bias, such as loss of crystallinity and loss of photoluminescence. I wanted to show a little bit of what goes on in my mind when I think about the perovskite life cycle. So we have here our perovskite. It is somehow in solution, goes through some processing steps, and we end up here in a steady state. And we would like it to stay there in the steady state. But unfortunately, things happen, and we end up somewhere over here. So what we want to do for our first goal is try to see what happens at this stage without interfering with the processes. So this puts a lot of constraints on what probe, what conditions, and what time frames we have to use. Because our probe has to be able to not interfere with what's going on. Our conditions have to be as similar as possible to what actually happens under operation. And if something takes a really long time, for example, if this takes 1,000 hours, we might need to perform accelerated testings in order for our experiments to be able to catch changes. In our case, we decided to use X-ray diffraction, photoluminescence, and impedance spectroscopy. And for the conditions that we decided to apply was to apply a high forward bias voltage in order to inject carriers into the perovskite layer, and also continuous illumination, so that we get this accelerated conditions inside our perovskite layers of a lot of excess carriers inside the device. And in order to isolate the stressors, we performed experiments in nitrogen room temperature gas flow. We have a second goal, which is to actually place a barrier here in order for our perovskite not to go beyond the point of no return. And in our case, we decided to use a molecular additive, 3-phosphopropionic acid, or H3PP, which is a well-known additive to our group. And going a bit further into the probe, we use X-ray diffraction. And this might seem very straightforward, but to do X-ray diffractions with all of these conditions is maybe not as simple as it might seem. First of all, we needed to build a homemade stage that uses a graphite dome around the cell that's placed here on this O-ring. And we have a nitrogen flow controlled by quite sophisticated gas system that allows us to have a controlled flow here inside, while we can still see the device with X-rays. We also have a white light LED underneath the sample that shines light through a quartz glass onto the sample from the normal operation side. And we also have electrical connections to the device so that we can apply a bias to it quickly, and we can use a computer, and we have a computer interface to both apply a bias to the device and also read the output from the device in the current. So if we apply voltage, we can read the current. Finally, to adapt for the time frame of experience, we needed to shorten the scan, because usually a XRD scan that we use is around 60 minutes in order to have good enough resolution. So what we decided to do is we shortened the scan to 15 minutes, but still including these important peaks, because by having this FTO 110 peak here, we could actually account for any misalignment between samples. So we're able to compare results between samples and also able to check that there's no misalignment issues going on throughout the experiments. And for all of this to happen, I really can't stress enough how important it is that we have our talented technicians such as Roque and Jessica for the development of these procedures. But the problems don't end here, because we also have to be able to apply a voltage bias in an area that we can see by the XRD. Because naturally, if we would just apply a voltage bias on top of our normal pixel cells with this type of electrode, we would get almost all of the bias underneath the pixel. And we cannot see through the pixels with our X-ray diffraction setup. And what we decided to do is first to create this finger-style electrodes to try to guide the field a little bit further. But we stumbled up, well, we had read this pioneering article where they used a thin gold layer to bias a thin perovskite film. And we talked to the authors and developed this further to full devices. So we have this device with this finger electrode, and on top of it we have a 7 nanometer thin gold layer. This thin layer is semi-transparent, so it's still connected, but it has a little bit of possibility for the X-rays to pass through it without too much interference with the gold. And this layer was evaporated by electron beam evaporation in order to have a better quality. The reason for this is that we noticed that if the quality of the electron beam was not good enough, you could easily have a lot of agglomeration and not an accurate layer. It's also sensitive for the time to perform experiments, because naturally, when you have such a thin layer, you will have some aggregation and oswald ripening over time. And we had to test how long our gold layer would sustain. We thought it's quite reasonable for it to be useful up to 20 days. But our experiments were performed 4 days after the fabrication, and if I'm not mistaken, 2 days after the evaporation of the layer. So we were well in the margin. Okay, so to summarize this, we now have a nitrogen flow, we have elimination source, we have electrical connections, and we have our non-destructive probe to see inside the full device. We also have adapted the time and electrode, and we can now bias an area and illuminate an area while we do X-ray diffraction on that volume. Okay. Finally, we also needed to develop quite a lot of automatic analysis around this, because we generate a lot of data from both the computer and the X-ray diffraction. This automatic analysis is available with the paper if someone is interested. Okay, moving on to the devices that we've tested. These are NIP devices with this perovskite quadruple, this perovskite composition, and they have we have the references devices, just very straightforward, that have a great stability in dark storage, ISOSD. And the modification is something that we had done before in the group, and this has shown to increase the stability of the devices. And we knew that this additive has a property to passivate the shallow defects in the device, this 3-phosphoroionic acid. And the additive is sitting at the grain boundaries inside the perovskite. When we investigated our devices that had incorporated the additive, we saw that there's a slight compression of the additive when of the perovskite when we have the additive. Our calculations were made quite straightforward through Bragg's law, and with Miller indices we could calculate the add value, and then we can do this Nelson-Riley regression, which gives us a more accurate value of the lattice parameter A. So additionally, apart from this initial compression, we could also see that there was a slight preferential orientation shift in the halide perovskite that's using the modification. Okay, so yeah, as I said, we cannot see the H2PP molecule inside the structure, but it must be located in the grain boundaries or at the surface. So just a short sidetrack a little bit about strain. Strain is the deviation from the most favored lattice configuration or symmetry energetically when the crystal is responding to some sort of stimuli. So this can be either internal or external stimuli, and there could be elastic strain or chemical strain. So in our case, we are likely seeing internal stimuli with elastic strain. Strain has been modulated through several strategies before, including additive engineering, and if not cared for, strain can have large consequences on the optoelectronics and activation energies for both ion migration and phase transitions, and also on the interface properties of the devices. Finally, strain can be isotropic, meaning that it expands in all directions at the same time, or it can be anisotropic in a way that if you, for example, have a glass and the glass is cooling down after annealing, the glass has a larger thermal expansion coefficient, so it will contract more than the layer that's on top of it. And this usually leads to a compression in the in-plane distances, but an expansion in the out-of-plane distances, as you can maybe imagine from this drawing here. I mentioned this because there was quite a discussion about with our reviewer for this paper about this, and we ended up performing some interesting complementary experiments. So our belief is that the perovskite is not affected by residual strain after fabrication, because there are so many layers inside the stack that should be able to compensate for any strain that's occurring because of the large thermal expansion coefficient of glass. So we performed cheese scan measurements, which requires some additional tuning of the X-ray diffraction machine, but then we tilt the sample. And when we do this, and we add this tilting, we can clearly see that this Poisson effect, where this the FTO layer is getting strained by the cooling of the solid glass, is occurring. So we have a more expanded FTO close to the 90 degree, like in angle, and then when we tilt the sample to another T angle, we see how it's getting more compressed. When we investigate the perovskite peaks, on the other hand, we don't see this. So thereby we've proven that there's no residual strain in the perovskite layer in full devices. And this is really an important observation, I believe, and a motivation towards more investigation of full devices, because what we see on just a substrate and a thin film might not be the case in the full device. So moving back again to our samples, we saw this initial compression. We also made an adjustment to align for this FDO111P to make sure that what we saw was statistically viable, and this compression did not seem to affect the optoelectronic properties such as the band gap or the JV curve. And we also couldn't see any changes on impedance spectroscopy in the recombination resistances, or after fitting with this equivalent circuits, we couldn't see much difference in the low frequency time constants, which are related to the mobility and or density of ions inside the device. We could see maybe a small difference in the low voltages between the reference and the modification. So in the following plots, the reference is the device without HGPP, and the modification, it has HGPP in the solution before crystallization. Once we applied our accelerated conditions of 2.5 volt and in nitrogen atmosphere and 0.3 sun, what we saw was really interesting. This is a very busy slide because what we see it all at the same time, and and I wanted to show it all to you all together. But what we see is that first there's a small increase in the current followed by a sharp decay. And this is seen both for the reference and the modification, but a little bit in accordance to the improved stability of the modification. In the modification, this happens later. We also see that all of the perovskite peaks shifts to the left. And this is corresponding to an expansion of the perovskite lattice. And we can approximate through the Nelson-Riley regression that this expansion of the reference is around 0.02 angstrom in the lattice parameter A, and in the modification, it's around half. It's also important to note that the timescales that we see for the expansion are very similar to the timescales that we see for the decay. So it's very probable that these effects are interconnected. The effects of applying a bias, we tried it as well at 1.2 volt, and we can see that same effect happens, but it's bias dependent. So in that case, I think it took 4 or 5 days for it to start to decay. And this happens in both modification and references devices, as you've seen. So our molecule didn't prevent this change from happening, as a little bit contrary to common understanding that once a compression is induced, it should prevent the degradation due to strain. So in impedance spectroscopy, what we did was we did impedance spectroscopy at a modulation of 10 millivolt, and we scanned like a steady state JV curve here. And what we can see is that over time, there's this injection barrier forming, which is representing as a resistance at the injection producing voltages. And this is happening more and more the longer time that we subject the perovskite solar cells to the bias. Interestingly, we also see that this low frequency tau, or low frequency time constants from the impedance spectroscopy is increasing fourfold. And this really indicates that as the perovskite lattice has expanded, the ion mobility of devices is a lot higher. Okay. For photoluminescence spectroscopy, what we see, what we did is exactly the same experiment. So we have our device connected to electronically and in the nitrogen flow, and we add a 2.5 voltage. But in this instance, the illumination is the laser from the photoluminescence. So it's a pulse laser of 153.6 nanometer. And what we see is that when we apply the conditions, the peak of the photoluminescence peak shifts to the left. And this is happening in both the reference and the modification. And first we see a very strong electroluminescence, and this is followed by gradual loss in the photoluminescence. And what we did is we fitted this to a Gaussian and could see how this changed over time. So as I explained, with the intensity, we see an increase followed by a gradual decrease. And for the band gap, we can see that there's an increase in band gap that's very well corresponding to an expansion of the lattice. The same thing is happening in the modification. So what we see is, that's very interesting, is that over here, we start to see the same trend for the current. So we start to see the current go down. And during this drop on the current, we also see that there is again a small increase in the intensity of the photoluminescence. And there's also a return towards the red in the photoluminescence, so towards a bit of a lower band gap again. And this we interpret as a reduction of the internal electric field inside the device that's caused by this injection barrier that should be happening at the interface. So we're very happy that all our experiments supported each other, and that, well, the phenomena in general seems to be the same for both reference and modification. We also saw that that devices that were biased for a long time tended to short circuit. So to summarize, we saw that the current decay and the decay in performance of the device, it was really related to this expansive strain. And we could see that the modification kind of was in a more compressed state at all times, but it didn't prevent the change from happening. Once the lattice was expanded, we saw that there's a large increase in the ion migration, the possibility, and we can see that this seems to lead to an injection barrier forming at the interface. And these results, both with the expansion and with the barrier forming, were also supported by photoluminescence. So our mystery feature here seem to depend on expansion of the perovskite lattice of around 0.02 angstrom in the A value. And say already said. So to sum it a little bit up again in a graphic, we have this our device, and in the expanded state, ions are more free to move. This eventually leads to the barriers forming, and we no longer have a well-functioning device. And here we likely have a lot of irreversible degradation. Okay, so I think that's almost time. I just to conclude again, our methods that we have developed seems quite easy to use. It's non-destructive, and we could probe the full devices. So we could see some internal properties, but we could also measure the level of degradation in situ. The lattice parameter increase seems like this first step of degradation in our perovskite solar cells when we apply these accelerative conditions. And the expansion seems to facilitate the movement of ions. And with the modification, we could not prevent the degradation, but it seemed to have some better resistivity to the changes. So the question is if this will happen with other additives that also produce a compression. And we also added that there is no residual strain in the halide perovskite layer for our full devices, and that these strain and interfacial properties are very likely connected to each other in a larger picture. Okay, so here's the publication where you can read all about it. And with that, I really like to thank everyone who's been involved in this work. Sonia, Masoud has made advices. Sonia, she has been a very supportive supervisor and very much part of this work. Also, Monica, for supervising and for leading our group. All of the people in the NMP group. I want to thank Sandy for help with the XRD analysis and for help with complementary experiments. Of course, all the technicians that have been helping at ICN2. And I also want to thank Damaso Torres for his help with some of the graphics for this talk. And of course, thank you for your attention and for your future questions.